Hello, good people. Welcome to the last part. And in this last video, we take a look at different cross sections because we've been focusing a lot on squares, right? And so, what happens if my cross section is not a square? And so, we're going to do the same region. This is the region that's trapped between the function f of x and g of x. They intersect at 0 and 1, 0, 0, and 1, 1. We're going to find the integral expressions that will find the volumes for each of these solids, but we're not going to evaluate them. We're not looking for the answer, but we're going to do it with different cross sections. So it's always going to be the same shaded region. So we're always going to be putting our cross sections in here, but it's going to be different shapes. So kind of like the pictures that you have at the beginning of your notes, right? It's the same shape, it's the same function, but different cross sections. Okay. Region R is the base of a solid. For this solid, each cross section perpendicular to the x-axis, so everything's going to be in terms of x, is defined as the shapes below. Write but do not evaluate an integral expression that gives the volumes of each solid. All right, here we go. This one we know. The area is side squared. The function, well, if I draw my representative rectangle this way, this is a top minus bottom situation. I'm doing it perpendicular to the x-axis the way they asked me to, and the length is top minus bottom. So then this is just going to be f of x minus g of x. We'll do that color. And we're going to square that because that's what the formula says, right? Take the side of a square and square it. Okay, so we did that. So therefore, to find the volume, we're going to take the integral of this thing. And so let me just do it in a different color here. Let's do it in purple. F of x minus g of x quantity squared. We're starting at 0. We're starting to stack our rectangle or our slices from 0 all the way to 1, from 0 to 1, dx, and we're done. That's the setup for number 1. Okay? Setup for number 2. Can we do it with quarter circles? Well, what's the area of a quarter circle? I know the area of a circle is pi r squared, so a quarter circle would be divided by 4. This is the blueprint that I need, right? So my area function is going to be pi 4 r squared, but what's going to be in that r? This is where I have to be careful. I need to find the radius, but if you think about it, if this is a quarter circle, then this, and I'm going to try to draw it as best as I can, the quarter circle is going to look like this. It's standing up, right? So if this is a quarter circle, this length of the rectangle is the radius. So therefore, this is just f of x minus g of x. So if I want to find the volume of this shape, of this three-dimensional object, that's the integral from 0 to 1 of pi over 4 times f of x minus g of x, which is the radius, squared. Dx. Don't forget the dx. Now, I like number 2 because it makes us think, what exactly is this representative rectangle measuring? Well, in the case of number 2, if I'm drawing quarter circles, that is measuring the radius. But be careful, because when I get to number 3, now I need semicircles. Okay, so let's set that formula up. The area of a semicircle is pi r squared divided by 2. So therefore, the area function is pi over 2 something, or radius, I shouldn't say something, but radius squared. But when I come draw this picture over here, and let me see if I can get that back. Let me erase these parts. Yeah. Then the semicircle is going to look like this, right? This length is not the radius anymore. This length is the diameter. So I'm going to have to say f of x minus g of x, which is the full length, but then inside of my squaring, I need to divide that by 2. Do you see why I had to do that? In a semicircle, when if I were to place a semicircle here, this whole thing is the diameter of the semicircle, but I need the radius. So I need to take this length, which is f of x minus g of x, and cut it in half. That's the radius squared, and then pi over 2, which is part of the formula to find the area of a semicircle. Great, now I can do the volume. If I were you, I would not simplify anything. I would just say from 0 to 1 of pi over 2 times f of x minus g of x, everything divided by 2 squared dx. If you look closely, the formula for the area of a semicircle is right here, pi over 2 radius squared. And you're done with that. So far, so good, right? Okay. Find the volume with a cross-section that's a rectangle with height 4. Okay, how do I find the area of a rectangle? Base times height, right? Base times height, except they're telling me the height is always 4. So I don't need to put this. I can just say base times 4. Oh, so therefore, if I erase this semicircle, this is the base and the height is 4 jetting out towards me. That's 4, but that's the base. So if I'm going to build the area function is base, which is top minus bottom, times 4. That is the area function, right? The blue rectangle that you're seeing in the picture is the base. The height is always 4, and it's projecting out towards us. So base times height, that's how you find the area of a rectangle. And now we can find the volume. The volume is the integral from 0 to 1 of f of x minus g of x, everything multiplied times 4. You can even put the 4 in the front. You can put the 4 outside the integral. But this is how you would find the volume. Notice my limits of integration are always from 0 to 1, 0 to 1, 0 to 1, 0 to 1, because this region is trapped between x equals 0 and x equals 1, right? So it's in that window, in that interval. Do you see how it all depends on what the shape of my cross-section is? That's going to determine how I'm going to set up my area function, and then how I'm going to integrate that area function. Let's go to rectangles with the height that's twice the base. Ooh, okay, so how do I find the area? Area is normally base times height. The area of a rectangle is base times height, but the height is twice the base. So I can erase the height and say base times 2 times base. Or I can say 2 times base squared. That'll give me the area of that rectangle. So multiply base times 2 times base, because the height is twice the base. But we can multiply base times base and get base squared. So therefore, my area function is, let's put the 2 in the front here, f of x minus g of x. F of x is top, g of x is bottom. When you subtract f of x minus g of x, that gives you that length, which is the base of my rectangle. But I'm going to square it and then double it. And that's how I find the area at any given x value. We want the volume, so all we need to do is integrate. Volume is the integral from 0 to 1 of all of this business. Squared dx. Pretty straightforward, right? And then finally, we get to number 6. Isosceles right triangles with one leg as the base. So I'm going to try to draw this. Okay, isosceles right triangle. What do I know about an isosceles right triangle? Isosceles means 2 of the legs, or the 2 legs, have the same length. So if this is one of them, then the other one goes up, and then the hypotenuse goes this way. But here's what we know: this length and this length are the same. It's jetting out. I know it's kind of hard to see, but it's jetting out towards us. It's standing up. So therefore, if you think about it, this is the shape, but this and this are the same, and this is the representative rectangle that we just saw on drawn in all of the figures. So therefore, let's see, area of an isosceles triangle is 1/2 base times height, except the height, because it's a leg, is the same size as this leg. So I can just erase this and say 1/2 base times base, which is 1/2 base squared. And my area function, therefore, is going to look familiar. F of x minus g of x, and then squared. So once I do my volume setup, I can use the integral from 0 to 1 of this thing, and I will be done with that expression. This will find for me the volume of that three-dimensional shape. Look at all the differences. Even though we're using the same base shape, the region doesn't change. What changes is the expression, is the slice. And because I'm using a different slice, I'm going to use a different area formula. And that's why I have all these different volume integral setups that are look similar, but they're not, because it depends on that slice that we take. That's volume by cross sections. It's a pretty graspable idea. I feel follow the process, and you can't go wrong.